think I have a chat. Okay. Oh, that was a time ago. All right. Any questions? Why can't the green term be put into A? Yeah, that's actually a good question, because why can't the green term be put into A? So what is actually special about A is that the matrix A is multiplied on this unknown U. And A is multiplied on something that is not known, while the entire green term is actually known ahead of time, because this right boundary is not something we need to determine, but something we already know ahead of time, right? So, so this cannot really be put into A, because nothing in the green term is multiplied by the set of unknowns U1, U2 to UN minus 1. Instead, it is multiplied by something known. So maybe my answer is yes, the A actually can be put into the matrix, but then when you try to solve this equation, you have to separate the last column from the rest of the matrix and really move it to the right-hand side. Yes, okay, so another question is, could it be combined with B then? The answer is exactly yes. So how do we solve the matrix? Is going to be A times U equal to my original B minus this A times A dot N. All right, so this is how we would actually go ahead and solve the system. Yeah, good question. Any other questions? All right, so let's go to MATLAB and try to solve it. So this is a continuation from what we have written down in the last lecture. So let's actually go back to 10 elements, okay, so that we can see things more clearly. And again, we are going to be making this kind of a random elements. Okay, so let's actually put a separation here, and let's run this part beforehand. So we get a bunch of x. We get an x that is a pretty random, right? You can see they are not uniformly spaced. Okay, and you can see in the last lecture we actually started by making an A that is n plus 1 by n plus 1. Actually, we already kind of prepared for having this extra column at the end, and also potentially an extra column in the front, right? That is if we also happens to have a boundary condition on the left. So we can see how that works in the beginning, later on. Okay, and now you can see that we are only looping through the middle to fill in the diagonals. But if we also want to include the diagonal for the, well, actually in this case, we actually don't need to include the diagonal for the first and last element, because we only need one additional column at the end, right? So what we really need is the following. So let's actually illustrate it over here. The matrix A originally was a tridiagonal structure. That's something we discussed on Monday. And we need to add one additional column on the right. Okay, this additional columm on the right is the integral of d phi I dx with d phi n dx. And what is d phi n dx? D phi n dx is this function, right? It goes all the way from xn minus 1. It stays 0 all the way from 0 to xn n minus 1, and then goes linearly up to the value of 1 at the end. So if you look at the derivative, it is only non-zero within the very last element, right? It is only non-zero over here. So when you take the integral with the when you multiply it with the derivative of another basis function, another head function, there is actually only one head function for which such integral is non-zero. Which one is it? Okay.
Phi n minus 1.
Yes, only phi n minus 1, which is this function, would make it non-zero. And the formula would actually be exactly the same. I mean, so basically I would have only one entry here that is non-zero, and I have 0 anywhere else. So basically I only need to calculate that one additional entry for the last column, right? And the value is actually exactly the same. And this value for the off-diagonal term is from xn minus 1 to 1, because I only need to integrate for this non-zero overlapping region. And the value is negative 1 over 1 minus xn minus 1, right? Squared, but I'm also integrating over a region that is of length 1 minus xn minus 1. So that basically cancels with one of these squares, and I have negative of 1 over 1 minus xn minus 1. So this is the very last entry. So, okay, so I don't need to modify my diagonal terms, and on the off-diagonal terms, I need to add one more. So a of n elim, so that's the row, and n elim minus 1. So that's the last column, would be equal to, I'm just going to copy this. And here my I, sorry, plus 1. Here my I is actually going to be n element plus 1, and I minus 1 is n element, right? Or maybe another different way to say it is a of n minus 1 end is equal to 1 divided by x end minus x end minus 1, right? Maybe this is a little bit more clear. So let me comment out this one. Okay, so now we have also the last column. So before we actually get rid of the last column, let me say a right-hand side is the a that has to be moved to the right-hand side is going to be equal to a. For the rows, I'm still going to be taking from 2 to n minus 1, but for the column, I'm going to be